Okay, hello physics students. This is the third video for the last assignment. I thought it would just be kind of a shame for us to just barely mention the mass energy equivalence, or E equals mc squared, without really doing it in a little bit more depth, even if the AP exam doesn't. So I think we'll do it in a little more depth than you might have if you tried my extra credit assignment back in Algebra 2. You might have already seen this a little bit, but anyway, if you didn't, no worries. So I'm going to try to explain some of the stuff in the book, but you should try reading at least the non-example parts of the book in this section. It's only a couple pages, so make sure you do that as well if you can. All right, so relativity is something we're really just not going to do this year. There's special and there's general relativity. Special relativity has to do with things that are not accelerating, and it's certainly a topic we could learn. It's just not on the AP exam, so I don't think we're going to take the time. General relativity is what Einstein worked on. It took him a lot longer. So in 1905, he came up with special relativity for non-accelerating reference frames, which is pretty much most of the stuff we've been doing this year. It's the stuff that has constant acceleration, right? Like the kinematic equations. General relativity is much more difficult, involves heavy calculus, not just like Calc 1 or 2, it's beyond that. So anyway, when he came up with E equals mc squared, it was actually after he had already worked out some ideas on special relativity, and basically what he figured out was that time was a thing that could slow down, and that the speed of light was what was always constant, and that had effects on a lot of different things, including E equals mc squared. Okay, so E equals mc squared is only like part of the story. So you're going to learn that when something's not moving, its energy, or E sub 0, which means that since it's not moving, its rest energy is equal to its mass times the speed of light squared. But relativity comes in once you start moving. So once you start moving, it's not just mc squared. It has more than that. So down here it says total energy. So the total energy is, in other words, the rest energy, mc squared, and sometimes they put a sub-zero here, and then plus the kinetic energy. So kinetic energy has to do with how fast you're going. So you can see up here that the kinetic energy has what in it? It's got m in it, that's just a fixed mass. It's got c's in it all over the place. Those are just fixed speeds of light, right? Just numbers. The only variable that kinetic energy depends on is this guy right here, this velocity squared term. So this thing looks really complex, but you've got a nice graphing calculator which can handle putting it in pretty easy. The idea to understand is this kinetic energy term in the relativistic form of the mass energy equivalence only depends on how fast you're going. Okay? All right. So sometimes this is written, can you see how there's an mc squared in both parts? You can like factor that out over here sometimes and then just say mc squared, factor it out. And then this guy, the 1 over the square root stuff, that guy is a lot of the time just shorthand referred to as gamma. So it's gamma. If you factor it out of this term, you have 1 left. So gamma minus 1 is the kinetic energy. If you add up kinetic energy plus mc squared, so you get like mc squared, those parts right there and there cancel out. This part is the total energy. So can you see why it reduces down to this part right here? And that's another way to do the total energy. So don't let this freak you out. It's just got some weird looking stuff. It's pretty easy actually. Okay, so you can read more in the textbook if you want a little bit more detailed explanation than that, but it's not a big deal. You've got rest energy, you've got kinetic energy, which you can express like this, or with just that gamma, where gamma's got the variable in it, right? It's got the V, and then total energy is just a combination of those two. So pretty simple. Let's use it for a variety of purposes, and I think some of it should relate to exactly what we're doing in this last unit on atomic physics. Okay, so 26.8 talks about a pion's kinetic energy. So it says a pi to the 0 meson, so it's some kind of particle, who knows. It gives us its mass right here, and it travels at 0.8 c. So what's that mean? That means 80% of the speed of light. So they actually calculated that. How'd they calculate it? They went 0.8 times, if we did it, it'd be 0.8 times, and you need to memorize, of course, the speed of light is 3 times 10 to the 8th. So that gives you 2.4 times 10 to the 8th. Okay, so what we're supposed to do is calculate its kinetic energy. So let's write down what we're trying to do. And we'll do it with the relativistic equation right here, but then we'll also do it with just the classical equation. In fact, let's do it with the classical equation first. So half mv squared, right? That's the kinetic energy of something. So we go half the mass, which they gave us, times the velocity squared, and we get this many joules. So if we just didn't know anything about relativity, if this was before 1905 when Einstein came up with this stuff, we'd have said, hey, that pi meson particle, it's really moving fast, but this is how much energy it has. And we would be fantastically wrong, it turns out, because as you move faster, that's not the way it works. Kinetic energy changes. Velocity changes kinetic energy. Now, what you're going to watch after I do all these examples, what you're going to read is the little last page and a half or so. And it's going to talk about how for everyday stuff, in other words, stuff that's not moving really fast, like this meson particle, it's going 80% the speed of light. That's crazy fast. But for something that's not moving crazy fast, if it's like sound, like that's going 343 meters per second, that's how fast sound waves travel, right? That's not even close to the speed of light. So stuff that's moving like that, or ordinary planes and cars and people, most of the time you don't have to worry about relativity because this v squared over c squared term turns out to be negligible. So one of the problems which I really want you to pay attention to in your reading guide is the one that says why is that negligible, and I want you to use a limit, or you don't have to think about a limit if you haven't had a lot of experience with limits yet, but somehow you need to make that decision and to talk about why this reduces down to the classical part. In this problem, this guy's moving crazy fast, so obviously this is a really wrong answer down here. Let's see what the real answer is with Einstein's kinetic energy. So here's the relativistic equation. We can plug into that just as easy. It just looks intimidating. So we plug in the mass, we plug in c squared, there's that. We plug in the velocity again. So the it's not again, but we plug in the velocity down here. So the question is, where did this part come from? Crazy. There's your -1. This is the only weird part. So let's go down here and do this part in more detail. So that is the square root of 1 minus v squared over c squared. You could actually plug these numbers in. Plug 2.4 times 10 to the 8th, square it, and put 3 times 10 to the 8th and square it. Here's a nice way to do it, though. We said that this was also 0.8c, right? So we could go minus 0.8c squared, couldn't we? That'd be another way to do it, and then over c squared. So what would that be? Let me get rid of this guy. So then that would be, of course this is like 1 over, right? So I'm just doing the inside of the square root. So then we've got 1, what is 0.8 squared? So you might put that in your calculator. I just know it's 0.64. It's like 8 squared. 0.64 c squared over c squared, and then you say, hey, look at this, this reduces. So if you ever have a velocity in your problems in terms of c, do it this way instead of plugging in those big crazy numbers. You could do it with the crazy numbers, but it's really easy to make a mistake with parentheses in your calculator. So anyway, let's go back over here and say now that's equal to 1 over the square root of 1 minus 0.64. Do you see where they got that now? And they're calling it to the 1/2 because square root is equal to 1/2 power, right? Okay, so then you can put that in your calculator. And all that stuff in your calculator comes out to this many joules. Let's compare 1.4 times 10 to the 11th, negative 11th, 6.9. That's like a very large percentage error. I guess we could come up with a percentage error on that. I guess we could go let's do it. You know what? I think it's worth it on this problem. So let's do the percent error. How much error was there? So we go actual, which is the Einstein one, minus predicted, which is this other wrong one, over the actual. And I don't have this prepared, so I'm going to have to stick it in my calculator. Let me see what I get. Let's see, minus 6.9 times 10 to the negative 12. Pretty big difference, I think. Whole order of magnitude different, right? So it's got to be like double or at least like 50%. I got like 50%. So I got like 50.7% error. It's a pretty gigantic error. Not something you'd want to have if you were doing an experiment. Okay, so I hope that little example showed you a bunch of things. So I like that little trick that we used right here. You don't have to use that trick, but I'm sure it's going to be useful on some of the problems you have to do. Okay, here's another one. This one is basically what we just did in a previous video where we talked about uranium undergoing a radioactive decay and becoming thorium. So let's think back. Which kind of decay was that? If it went from this mass, it basically lost like about 4 protons or 4 nucleons. So I think that was an alpha decay, wasn't it, where it emitted a helium particle? Ah, there's the helium. It says right there. So plus a helium atom. So it says calculate the energy released in this decay. So this is the same kind of thing we did before, right? So the energy released in this decay is the difference. Well, let's just see. So they say the initial mass is this much, right, from the uranium. Then decay in mass. When you emit that, and you get thorium as the daughter, and the helium alpha particle. Remember, if we had like this little guy, and then that guy, you just do MC squared on. So I think that's what they did. So they took MC squared on that guy, and they got that this was the amount of energy released. We just did that problem, so I'm not going to do it in depth again here. Okay, let's see what else we've got. All right, this one says in a chemical reaction, this would be more the kind of thing you might do in chemistry. So it says when 2 moles of hydrogen and 1 mole of oxygen react to form a couple molecules, or, well, I shouldn't say molecules. Moles are not molecules, right? Moles are Avogadro's number of molecules. Anyway, so when you have 2 moles of hydrogen react with 1 mole of oxygen, you get 2 moles of water, and it says that this much energy is released. So they could also turn this around and say how much mass is lost in this kind of thing. This is like what Lisa Meitner did, if you remember the video from Algebra 2, when she first split the atom. So how much mass is lost? So in other words, we're looking for how much mass change happens. So change in mass is what? Okay? Alright, so I think we're going to use MC squared, so you can put a change on both these guys. And this time we're solving for m, so we divide by c squared. So you see what they did here, pretty easy. Why is this negative? Why is this energy negative? Because energy is released from the 2, so that should be negative, right? C squared is c squared, pretty simple. So you get that this much mass, and it doesn't seem like it's a lot, but remember, a lot of mass can produce, a very small amount of mass can produce a large amount of energy, like these 484 kilojoules. So the question is, how tiny is that in comparison? Well, let's just think how tiny is that in comparison to what actually happened here. So it said 2 moles of hydrogen. 2 moles of hydrogen weigh this much, because if you remember from your periodic table, it has a couple things in the periodic table. I guess I should have grabbed a screenshot of that too, but let's just think about it. So if we flip back in the back of your book and you look at like hydrogen up at the top, it says hydrogen, it says like 1, and then below that it says like 1.000794, and then it has something about its chemistry spin orientation, which we're not going to do in this class. There's a lot of information here. If you recall, what we just learned is that this guy is the atomic number, which means protons, right? This guy down here means a lot of different things. This guy means its atomic mass, which gives you like the number of nucleons, right? But what it also tells you is how many, it also tells you the chemistry thing. So it's a packed full of information. So this also tells you that there's 1 gram. It's called its atomic mass for a reason. It means it's 1 gram per mole. So in other words, the reason this is 0.002 is because it said we had 2 moles of hydrogen. So 2 moles of hydrogen would mean 2 grams of hydrogen. Isn't that 2 grams right there? Yeah. And if you look on the periodic table at oxygen, it says like 8 protons, and then it has like, I think 8 neutrons, can go 16 minus 8. But that atomic mass number, besides telling you about the neutrons, also tells you that it's like 16 grams per mole. So we said there was 1 mole of oxygen. That's why this is 16 grams. So the total um, uh, from those two reactants, the total product mass is going to be this heavy when you get the water out. So if it's that much, and you compare this guy with 10 to the negative 12th, I mean, it's hardly any mass that's lost. I mean, 10 to the negative 12th is like 0.0000000, way out there. It's a very small mass change. So this is the kind of small changes that occur in chemical reactions that people didn't detect until after Einstein. Okay, I'm getting a little long-winded in this video. Let's try to finish. One last question. This one says you've got a proton. It says a Tevatron accelerator at Fermilab. So Enrico Fermi, I think, has been mentioned several times now. He's got the femtometer, a order of magnitude named after him. He's a very famous guy. He was like one of the primary scientists on the Manhattan Project, an experimental and a theoretical physicist, very rare. Anyway, if you see stuff about him in the book, it'd be nice to read that. But the whole point is that it says a Tevatron accelerator can accelerate protons to have this much kinetic energy, a tera electron volt. It's a lot of electron volts. So it says, what's the speed of such, oh, not an electron, a proton. So if you accelerate that proton to have this much energy, how fast is it going? So, well, obviously that's probably pretty fast, so we're going to use the relativistic formula, not the classical one. And we're going to say, okay, put 1 times 10 to the 12th over here, and solve this bad boy for E. This is, excuse me, for V, for the velocity. We want the velocity. Okay? So it's just algebra. Don't let this screw you up. I give them problems like this in Algebra 2, so you guys should be able to do it too. So if we're going to solve this for V, hey, that it's inside that gamma thing on the bottom. Better multiply the square root up there. Okay? Then we probably better square both sides to unlock the inside juiciness. So square both sides. That's what they did, right? Let's see if they did anything weird. Then we probably should subtract 1, I'm thinking. Subtract 1 and divide by negative 1. I think they did that in the same step. So they went minus 1 and then they divided by negative 1 to make this plus and this minus. See that? Then you've got to multiply by c squared. Did they do that? I don't think they did. I think they actually plugged in numbers here. So they plugged in that kinetic energy from the very beginning right there. They probably did mc squared. So how'd they come up with mc squared? I bet they said the mass of a proton, pulled that out of the chart. C squared is c squared, and they got this. Okay? Or they did it right here. But they didn't really show their work, so you could do that yourself. Okay? Anyway, so we get that. That's where this came from. So that's just mc squared. And then I think that you need to multiply by c squared and take a square root. So we take that. I don't like what they did after that. Let's clean this up. So they didn't show their work very good, but after that they let's go over here. So they said v squared equals that 1 minus, let's just call this stuff squared, and that whole thing is multiplied by c squared, and then the final step is to get rid of this squared by taking the square root. We don't really need to worry about plus or minus because we just want positive stuff. So square root of c squared is going to be c, and then you're going to have square root of 1 minus stuff squared in there. So I think that this algebra looks a little scary, but it's pretty easy. I don't know. If you can do algebra, you can do this. So hope you found this useful. Make sure you watch the part about when you need to use relativistic equations and when you kind of don't, which is like right down here, like the next page or so. Okay, and then we'll go on and look at fission and fusion in the next video. See you next time.